Okay. Now that I have most of you here, let's get started. Okay. Let's get started, you guys. All right. Let's see if you have a little bit more energy today as we talk about still energy and matter. All right. Let's recap. What are the different species of matter that can be analyzed using spectroscopy, Ingrid?
Atoms and molecules.
Absolutely. So they can be atoms, like your atomic absorption lab, analyzing elements, and they can be molecules, everything else. Name the different forms of radiation matter interactions. What kind of interactions do we have? Look alive, people.
But that kind of relates to like the moisture lab where we're having like microwave interactions with like samples, or is it something else?
I'm targeting something else. There.
Isn't it like the diffraction?
Yes.
Yeah.
So
yeah.
whenever you have matter-light interaction, you can have a diffraction, you can have emission, you can have reflection, you can have absorption. Very good. So absorption, emission, diffraction, refraction, reflection, light scattering, all of this are interactions with matter. What are the spectral regions most relevant to food analysis?
Isn't it IR all the way through ultraviolet?
Yes, so IR, visible, and UV. We don't care about anything else above and below these regions in food analysis. What are some applications for spectroscopy, spectrometry? Go ahead, Bianchi.
Qualitative and quantitative.
Qualitative and quantitative. Under qualitative, we can do identification, detection, looking at contamination or forensics, structural elucidation, and of course, a lot of the applications are quantification, where we do compositional analyses to determine concentrations. What is this difference between electronic and vibrational energy, and to what spectral region each corresponds? Electronic energy versus vibrational energy. Go ahead, Sarah.
Electronic energy refers to like the jump between energy states, like ground state and excited states.
Of what? Who jumps?
The electron.
The electrons. Okay.
And vibrational energy is like the movement of molecules themselves, like in relation to bonds.
Exactly. The movements of bonds, the vibration of bonds that are in constant vibration of stretching and bending. And then when an energy is absorbed in the right quantity, then the vibration changes and the molecule goes to an excited state. In electronic, the name implies electrons get excited, either the valence electrons or the electrons within a bond, and they jump to a higher energy state or a higher shell. Okay, and then, all right, so we answered half of the question. So electronic energy, which region of the spectrum applies to electronic energy? Go ahead, Katie. Absolutely. So in UV vis, the energy states matches the electronic energy levels. And in vibration energy, the IR energy levels matches the allowable vibrational levels within a molecule. And which carries more energy, electronic energy or vibrational energy? Ash. Electronic, absolutely. That will answer a question below. How does the wavelength impact frequency and energy? So, go ahead, Taylor.
As a wavelength increases, the frequency and energy are decreased.
Absolutely. So when you have shorter wavelengths, you have higher frequency because you have more oscillations in a unit time and a unit distance. And that means you have more energy. As the wavelength increases, you have less frequency and less energy. Therefore, vibration energy is IR. So IR wavelengths are longer than UV wavelength and then visible light wave. What's the difference between absorption and fluorescence? So, and you all know this. So let's see who is the brave soul. You want to go for it, Jason? Yeah. It emits light. All right. Does it emit light at the same energy that is absorbed, or higher or lower? Lower, because always the molecule goes from excited states, or the atom, from excited state to ground state by dissipating heat. There's always a dissipation of heat. Some atoms and some molecules dissipate heat and emit energy. So the energy is less than the energy that has been absorbed, basically. Always. And some molecules and atoms don't fluoresce, go down to ground state by emitting heat, by just giving up heat rather than emitting light. All right, cool. You're ready to move on. All right, in UV spectroscopy, we have absorption and fluorescence. We have different applications where we focus on absorption spectroscopy and different applications where we focus on fluorescence spectroscopy. And we said that there are qualitative and quantitative. And sometimes we have internal signals. That means the compounds of interest are chromophores. That means they're naturally absorbing of light. Sometimes it's not like that. We have to chemically induce it. For example, in carbohydrate analysis, you're going to learn the phenol sulfuric acid assay, where you're measuring the glucose, but glucose does not absorb light. So we reacted with a compound, and then it becomes another compound that absorbs light. And we relate the absorbance to the concentration of the original molecule. And we sometimes do quantification of macro components like carbohydrates via that method that I explained, and you will be doing it in lab. Quantification of micro components, when we cover vitamins, you'll see that there is a fluorometric method specific for thiamine. There are other applications, obviously, for fluorescence. And we'll talk, at one point, we'll talk about allergens and different methods of detecting allergens. One of them is the enzyme-linked immunosorbent assay, which is ELISA. In ELISA, you have an antibody and you have an antigen, but you label the antibody with an enzyme, or you label the antigen with an enzyme, and then you add a substrate, and you get a product that absorbs light. And then you can determine the presence of allergen, and you can quantitate if you have standards. So a lot of applications of spectroscopy, a lot of the upcoming chapters will cover spectroscopy. So therefore, we're learning about the principle here. So few things you need to remember. This might come in a quiz, that exact drawing. So you have incident B. P0 is incident beam. P is transmitted or exiting beam. And then you have a sample in a cuvette or a test tube. In there, B represents the length of the path of light. So the light is going through your cuvette, and the B is the length that the light goes through. C is the concentration, which we are after, and A is absorptivity, which is very unique to the compound. So we're going to learn about the relationship of A, B, C to absorbance. And then when we determine concentration, we usually look at the linear range of absorption concentration. So the relative transmittance, that means the transmittance of light, is correlated to analyte concentration, but it is not a linear relationship. So the light transmitted is not equal, or the absorption is not equal incident beam minus transmitted. Talked about that last time. Light can be scattered, can be reflected, can be absorbed by other interfering substances. So we cannot get the absorbance of a compound just based on subtraction. So the transmittance is a relative value. Relative P, which is the exit P or transmitted P, to the incident P. And percent transmitted is this ratio times M. This is not linear to concentration. So we do not use percent transmission to determine concentration. We like linear relationships. They're easy, they're less of a hassle, and we want to correlate, we want to determine quantification using linear relationship. So absorbance, on the other hand, have a linear relationship with concentration. And absorption is the negative log of transmission. Okay, we don't care. We don't care about that. We know it's a relative log of transmittance, fine. But what I want you to remember that transmittance is not linearly correlated to concentration. Absorbance is. That's what I want you to know. I'm not going to care about the equation here. I just want you to know what transmittance is, what absorbance is, and which can be linearly related to concentration. So that's what I want you to learn. And of course, I want you to learn or remember Beer's law. I'm sure you've had it in the past, maybe in high school physics or here. But Beer's law is the relationship between absorbance and concentration, taking into account absorptivity and the distance. So this you need to remember. Okay? Absorption equal ABC. First three letters of the alphabet. C for concentration, A for absorptivity, easy. The only thing that you might forget, like what is P stands for? P stands for the length that the light passes. So concentration can be in any unit, molarity, millimolar, milligram per milliliter, percentage, anything. The concentration can be anything based on how you prepare your standards and where the linearity lies. Sometimes linearity lies at really low concentrations, parts per million. Sometimes linearity is good in percentage. So it really depends on where the linear range is. So B is the length through the solution, and the unit of the concentration dependent on how you prepare your concentration. The length is also always in centimeter. And then the unit of absorptivity is basically the inverse of centimeters and the concentration. So absorbance does not have a unit. Okay? We call them units of absorbance, but you don't have a unit because the absorptivity is the inverse for taking into account the unit of concentration and the unit of distance. All right, absorptivity, when the concentration is in molarity, you'll hear the term molar absorptivity. So when you hear the term molar absorptivity, then your concentration is either in molar or millimolar. It's also called, that's question mark, it's called, I'm blanking, my brain went numb right now. What? Chemo brain, sorry. Wait a second, I'm gonna get it. Molar extinction. That's what it is. Okay. Where was I? Oh. Here. Okay. So when you hear molar extinction or molar absorptivity, that means the concentration is in molar or millimolar units. Okay. So think about this for a second. And what do you come up with? Give it your best guess. It's okay if you have a wrong answer, just try to think about it. Is absorptivity dependent on any of these, some of these, or all of these? And why do you think? Nobody's gonna be. Yeah, okay, Carol.
Molecular properties of the species.
A is correct. Molecular properties of the species. Every molecule have a unique property that allows them to absorb light at specific wavelengths. What is, okay, Kevin?
I'm gonna add a C to that.
Adding a C to that is very correct, because sometimes the environmental conditions causes dissociation of protons, association, changes in temperature might impact the molecular characteristics, changes in pH. When the molecular characteristics are impacted, the way they absorb light is impacted.
And I'll also add B.
Thank you. Yeah.
I know the different molecules absorb light at different wavelengths.
Yes, and for the same molecule, you will have a different absorptivity at different wavelengths, because you have maximum absorbance and less than maximum absorbance at different wavelengths. So if I want to get the absorptivity, it's definitely based on the wavelength. So all of the above, molecular properties of the species, the chemical environment that might impact the molecular properties, and of course, the wavelength. We'll hold that thought. Okay, so we talked about not all light passing through get either absorbed or transmitted. We talked about that. We have reflection. So the light hits the wall of the cuvette, it gets reflected. Even sometimes light gets scattered when it hits molecules. Lights get refracted, might be. And also, some components we don't care for absorb light at the same way. So you have interference. So a lot of things happen. So therefore, you can't just say absorbance equals light incident beam minus exit beam. It can't be. So oftentimes, to correct for things, we have what we call a reference cell or a blank. So when you have sometimes you have a spectrophotometer that have a cell for a blank and a cell for your sample. And your blank must contain similar reagents that you put in your sample as much as you're able to. So the blank then is correcting for any absorption that can be due to interfering substances. So basically, you will have this corrected, so the transmitted beam will have mostly information based on the absorbed light. But again, it's not a linear relationship with concentration. That's why we have an equation to calculate absorption and from there concentration. Sometimes you don't have that reference cell, so you'll be using spectrophotometers in the lab and they're simple spectrophotometers. So what you do is you have a blank and you just put it before the sample at the particular wavelength. You would just zero the equipment. I think you did that for AA, didn't you? You had a blank where you zeroed. Okay, so yes, so a blank is run, and sometimes when you don't have a reference cell, you have to run a blank if you have like 20 samples. Maybe after every 5 samples, you want to recorrect to allow for reduction of noise, shifting, changes. Definitely, it's better to have a spectrophotometer with a reference. It's definitely the reference cell. Definitely avoid you having to re-zero every now and then. So Beer's law has deviations from it. So usually we try to have diluted samples. High concentration cause molecular interactions. And when you have molecular interactions, absorptivity changes.
I just have a quick about a part of this question, but on the machine, is there an actual like button that lets you blank it, or is the blanking all of this like a manual thing? You keep in mind what you're calculating.
Yeah, so you will be using spectrophotometers in the lab, and you'll know that when you put the blank, you will hit a button that says either 0 or read or something, and then it adjusts to 0.
Okay.
So when you put the blank, it adjusts the reading to 0.
So they can like drift over time?
It can drift over
Okay.
time, unless you have a reference cell and a sample cell. It's continuously taking into account the reference reading. Yeah. Very good. So yeah, so we dilute our samples. Oftentimes they're very diluted because you want to avoid molecular interactions, because then you would have interference. The molecules interact with each other, they will affect their absorptivity. And then you'll have deviation from Beer's law. We need to figure out different molecules require different concentrations where you minimize molecular interaction. So we just have to figure out the best concentration range for different components. Chemical processes, we said that the environment, if you change the pH, if you're changing the temperature, you might get changes in the molecules, sometimes dissociation and association within molecules. And oftentimes to avoid that, we have a buffered system, especially if something is going to cause changes in pH and ionization. We run our assay in a buffered system. Polychromatic light. So number 1, Beer's law, you have to have monochromatic light. So because the molecules have different absorptivity at different wavelengths. When we looked at spectra, each molecule has a lambda max and absorb at different lambdas. So for quantification, you want to select one lambda and get the area under the curve of the absorption under that one particular lambda. You want to make sure your light is not polychromatic for quantification or for applying Beer's law. Another consideration is when you're measuring absorption, you want your solution to be clear, not necessarily like transparent clear, but it doesn't have cloudiness. It doesn't have molecules that will cause fogginess. Because the more molecules you have that it's cause them sample to be foggy, you'll have a lot of light scattering. And then you'll get erroneous high absorption, which you don't want. So oftentimes we have a centrifugation step to clarify your solution. So the color of the solution doesn't matter, but it shouldn't be cloudy. So we should always homogenize and clarify. We should always have correct blanks as much as we can that might have similar components to your sample. And also the choice of your cuvette or the holding container. So if you're measuring UV absorption, you don't want to use glass or plastic. For UV, quartz is the most expensive, you can use that, or pure silicone. For visible light, you can use glass and plastic. So basically, you don't want to use something that absorbs in the same region as your sample. Okay. Choosing the appropriate wavelength is very important. We need to know lambda max. So you will be determining lambda max for the carbohydrate assay that you're going to be doing in the lab yourself. You're going to be measuring a different wavelength and you're going to determine at which absorbance you're going to see maximum absorbance. You want maximum sensitivity and you want to select a wavelength where you have really a sharp peak, because you want wavelengths not to be very different that reach your sample. So you don't want like 300 and 310 and 320 reaching your sample. You want them around to be 311, 312, 313. It's okay if there is a very, very narrow difference, and you adjust that by your filter, by how much light you're allowing to reach the sample. So you can adjust the filter to make sure you have a very narrow bandwidth. You always calibrate the instrument. So you calibrate it for zero transmittance. So you cover the source of light, you block the source of light and zero the equipment and tell it this is zero transmittance. And then you don't have anything in your cell and you have 100% light going through the cell and you say this is 100 transmittance. So calibrating the instrument allows you to reduce what we call noise, absorbance that is not related to your sample. Okay, we talked about importance of linearity, where you want to make sure that your standards have a linear relationship with the absorbance. So this differs. So if you remember in your AA lab, the concentration for your calcium standard curve was different than the concentration for your iron standard curve. Because for different atom molecules, you have a specific range where the relationship is linear. So you do not want to measure absorbance of a compound where you have such a curve, because this is not a good prediction, or the Beer's law is not applied. So you want to see, where do I have linearity? Here, I make sure my concentrations are within that particular range, where I have a nice R squared for linear relationship between the absorbance and the concentration. Because if you have, and you want to dilute your sample where you don't measure up here, you don't measure at 12 millimolar or whatever it is you're going to get. If your sample has measurement here, you cannot say for sure your equation of the line is going to fit. So you have to dilute so that your reading is somewhere in the middle. So this is a big error if you have your, let's say, your calcium and iron that you measured in the lab. If they fell outside of the linear curve, that could be an overestimation or underestimation. You cannot be sure that your estimation was correct. All right, this is something that is a little bit confusing, but I'll try to explain it as simply as I can. But sometimes when you prepare your standards, you prepare them in water, in dilute acid solution, in buffer, whatever. But then sometimes your sample contains components that will interfere with the measurements, and your standards cannot account for that. So what we do, we call it using a standard addition protocol. We calibrate using standard addition protocol. So I'm going to draw that for okay. So you get your sample flasks and you put, let's say, 6 flasks. I'm just gonna draw, for simplicity, I'll say 4. Okay, 4 flasks. The concentration of the compound of interest is unknown to you. So you have the concentration of the unknown. You don't know that. So you are looking for concentration of the unknown. You dilute the sample and you put volume of the unknown that is the same in all flasks. 5 ml, 10 ml, whatever it is. And then you have here a flask containing your standard with known concentration. So you have your standard with known concentration. You add a different volume to each flask. So 1, so let's say you add 5 microliter, 10 microliter, 15 microliter, 20 microliter from the same stocks again. And then you make up the volume, whatever it is, 50 ml. All are made up to the same total volume. V total is the same. So now what you're doing is you're building a standard curve within your sample mixture, so that you take into account the interferences that you get from your sample. You also have a sample that doesn't have any volume in it, 0, so that you correct for that. So then you will have 0, nothing, and 4 different concentrations of the sample. Then you measure absorbance and you plot it against volume of your standard that you might use, and you get an equation with absorption. This is a constant, proportionality constant, path length times absorptivity. Volume of the standards, you have that. Volume of the concentration of the standard, you have that. Volume of the unknown, you know that. Total volume, you know it. You solve for concentration of the unknown. Question? Indiscriminate error. In other words, noise. You probably heard instrument noise before. That's what it is. Indiscriminate error. So you always have that, but you always target having a very small noise relative to your absorption. So you don't want absorption that is of something not relevant to be high in proportion compared to your actual sample. So you wanted to be able to test it with repeated measurement of a single homogeneous sample. So you can figure out your noise if you take a sample and you continuously measure it. Sometimes you get an absorption of, let's say, 0.812. Sometimes you have 0.814. Sometimes you have 0.808. So the difference in absorption is due to noise, and you really want it to be very, very small. And oftentimes you work with low concentration. The rule of thumb, you don't want absorbance to be much greater than 8.8 units of absorption when you're measuring absorption using spectrometry. If your absorption read 1.8 or 2.1, no, it's usually you have a lot of noise. You cannot do good correlation. You have to dilute, so your absorbance is between 0.2 to 0.8. This is the kind of the range that we would like to work with for absorption in a spectrometer. So I would say all of the above for this question. All right. Instrumentation. We've talked about monochromator before, right? So you have types of detectors where you have light that passes through a monochromator and a filter that selects a particular wavelength. So we've seen this before. So the light goes in, reflected by a mirror, grading system, diffracts, and then you have multiple wavelength light, and then you select your filter and the location to allow for a monochromatic light to reach the sample. So when you have a monochromator like that and a monochromatic light reaching the detector into an amplifier of the signal and readout, we call that photoacute detector. Very, very common in spectroscopy. But we also have a photomultiplier, PTM, we call it. Remember PTM because we're going to cover it in atomic absorption lecture next on Wednesday. So PTM, it's exactly the type of detector you have in the AA that we did in the lab, that we used in the lab. So what happens here, you have the radiation hits the cathode, and you have multiple diodes where the electron gets hit and hits another diode and multiplies, hits another diode, multiplies, another one, and then you get the really amplified signal, enhancing the sensitivity of the detection, instead of just having the only one cathode that reflects an electron onto the anode wire. So that is a phototube, and this is the PTM. Multiplies the signal, enhances the sensitivity, and that's the AA detector that you worked with in the lab. And then we have the photodiode detector, which we talked about a lot so far. I think you are experts in that now. In photodiode, which we used in the HPLC lab, you have the light, all of the light without diffraction hits your sample. So now your components are absorbing light over many, many wavelengths, depending on what wavelength they can absorb that. Then the light exiting has information about the absorbance of light of this particular compound. That light hits diodes, photodiodes, an array of photodiodes. Each photodiode can convert one particular wavelength to electrical signal. And now you get an electrical signal that reaches the detector and you have readout at different wavelengths. So you get absorption at different wavelengths. So the photodiodes or the array of diodes convert the energy of light to electrical signal, photo, light to electrical signal. You get that 3D dimension of data, spectral data, which you get absorption at different wavelengths. You have absorption, wavelength. In every fraction of a second, you get this spectra, three-dimensional data set. So the type of instruments that you have, we talked about single beam or double beam. So we talked about having one cell where you put your blank, take it out, and then put your sample and read it. Or you can have double beam. So the double beam is better to have, more expensive to have, but what it does, you have two holders, a reference cell holder and sample cell holder. So what happens is the light gets split, one going into the sample holder and one going into the reference. And then you get the transmitted light from both. And then you get the calculation subtracting the transmission of light from the reference. So you get the absorption corrected for already. You don't have to zero for a blank. That would be great to have, but you might not have it in the lab, so you would have to use a blank and zero before the sample and do that multiple times during your assay. This is the FYI table. So basically it shows you that different molecules have different lambda max, and people have found their absorptivity, molar extinction of molar activity for these different compounds. So sometimes you have references for the compounds that you're looking for. You can measure concentration without having to do a standard curve if you have the absorptivity, because absorption equals absorptivity times distance times concentration. But most of the time you don't have that. So you just have to do calibration. The last thing I have here is your fluorescence spectroscopy unit, which is a little bit different than a regular absorption spectroscopy unit. So in this unit, you have the same thing. You have a source of light. You have the monochromator, the wavelength selector. And then you have your incident beam that goes to your sample or sample and reference, whatever it is. Then you have the transmitted light continues on, we don't care for it. The emitted light is directed through mirrors to be perpendicular. And you have emission at different wavelengths too. And you have maximum emission at particular wavelengths. So you have another monochromator or wavelength select. The emitted light goes into that and you select for the emission or the wavelength that you have maximum emission. And that goes to the detector and then calculation of emittance of light, of force, we call it fluorescence, get determined. So always you have to select for two wavelengths. The first one here is where you have maximum absorption, where you have maximum sensitivity. And the second one here, where you have maximum fluorescence for maximum sensitivity. That's common. Sometimes you don't go for maximum if you have interferences and you want to avoid interference with other substance, you might go to a less ideal lambda But in general, we take maximum absorbance and maximum fluorescence. So always with fluorescence, you have to select 2 wavelengths to set up your instrument. All right, so that ends this. And on Wednesday, I have one more lecture of spectroscopy on AA, and then your midterm is on Friday. Now, what does it include? Do we all know what's on the midterm? Yeah, so everything except moisture. 2 lectures on moisture by Gary. All right. I'll see you Wednesday.